a quick review, and then we'll try additional questions. We'll try to finish chem bonding first. Then we move on to the revision. Okay. So I think I stopped here if I'm not mistaken. Okay, but just a quick one. So just a very quick one. The first part of my lesson here, we will do a lot of questions pertaining to hydrogen bond, right? So if you recall what I went through the last lesson, right? When you have a compound that's non-polar, right? For example, say that, for example, a simple one, like something that's non-polar, maybe like CH4, okay? So CH4 being non-polar, the intermolecular force attraction is only ID. We call it instantaneous dipole, induced dipole, right? Then when we have a polar molecule, for example, is like HCl. Okay, so anyway, this is non-polar. If you remember, okay, maybe I just go another one. So I think like if you remember the one that I did last week, this shape is tetrahedral, and it's actually non-polar. Because if I draw the dipole moments, they are pointing towards the Cl. Okay, they will all cancel out. It'll be non-polar, okay? Okay, and then it only has what I call ID, right? So if I have a molecule like HCl, which is polar, electrons are closer towards the Cl. This is delta minus, this is delta plus. So between two HCl molecules, this one is called PD. Right, PD, permanent dipole. But all polar molecules like HCl also has ID. Okay, it says PD and ID. Then after that, I mentioned the next one. Okay, the last one that we're gonna learn is what I call hydrogen bond, right? So how do I have a hydrogen bond? Again, the H must be attached to a F, O, or N. So this is the main criteria. Okay, this is a very, very important criteria. The hydrogen must be attached to F, O, or N. So when it's attached to F, O, or N, because all these are very electronegative atoms, F, O, N, right? So this very delta minus will make the H very delta plus, and then it will be hydrogen bonded to a lone pair on an F, or hydrogen bonded to a lone pair on an O, or hydrogen bonded to a lone pair on a nitrogen. Okay? So, but very important. I think the problem is some students they don't see it that way. But when you want to, how do you know whether a compound has hydrogen bond? First thing you look at is whether the H is attached to FON. That's the first criteria, okay? Make sure. Because unless it's attached to FON, then the H can be very delta plus. Right? So I guess if we draw like this, if any question that shows this, and then they show you, so is this a hydrogen bond? Is this hydrogen bond? No, right? Yeah. Because this H must be attached to FON. Okay, so that, so definitely this is not hydrogen bond. It's not, I say it's not. Got it? I know this H is attached to O, but sorry, I'm not talking about this H, I'm talking about this H. The H that forms the bond, the hydrogen bond, right, must be attached to a F, O, N. Okay? That's the big difference. Okay. So yeah, so this is hydrogen bond. Huh? Okay, good. Okay, so let's try some questions. Now we're going to do hydrogen bonding questions, quite a lot, and they're all very tricky. Okay, they're all very tricky. So let's try this one. Okay, let's try this, and yeah, we do together. Okay, read through, and as you do it, I'll go through. Do it, I'll go through. Okay. Okay, a lot of learning points. Okay, so write the formula of the ions present in KHS2. So part 2 chem bonding. Right, we type this then we do that again. Write the ions again. Okay, we are doing for those who just came in online. So yeah, Xin yeah. Okay, so we are doing from chem bonding part 2. This question. Yeah, there's only one cation and one anion. Read carefully. Some of you writing like 3 ions. There's only one cation and one anion. Okay, we're talking about all the questions we're going to do now. Hydrogen bond, because that was the last part that we talked about. So for some of you who just came in, right? Hydrogen bond, I just reiterate. Okay, you must look up for hydrogen. Hydrogen, right, attached to FON, and then hydro bonded to a lone pair on a FON. Okay, so this is a H bond. Okay, we're gonna look up. We're gonna do a lot of questions that pertain to hydrogen bond. Okay, which is a relatively strong intermolecular force of attraction. Okay, so try. Just give it like two minutes. Do the whole page and then move on to the next slide. Okay, you got a few slides to try. 1, 2, 3. Okay, at least 2 slides first. Okay, so the formulae of the ions, I think most of you are done with. So it's like KMnO4, right? KMnO4. What are the ions? The ions are K plus and MnO4 minus. All right, so what are the ions? Definitely it will be K plus, and the anion will be HF2 minus. Got it? Okay, so suggest a structure for the anion. Please, everybody draw a structure for this. All right, draw a structure for this. What kind of bonding is between hydrogen and F? Okay, if you want, you can even try to draw a dot and cross. If you're quite unsure, you can even draw a dot and cross. Can? Okay, what kind of bonding is present within HF2 minus? What kind of bonding is present between H and F? If you're not sure, you can try to draw the dot and cross. We're doing chem bonding part 2. Okay. We'll finish that before we can talk to the revision. Okay, this is tricky. Okay, this question is actually very tricky. Okay, there are limitations because hydrogen can hold a maximum of 2 electrons. And the limitation about fluorine is in period 2, maximum 8 electrons. So make sure you don't have for fluorine, better have not more than 8. For hydrogen, you cannot have more than 2. Okay, so that's why this question is very, very tricky. All right, go like that. Like 8. That's why it's tricky. Yeah, just give everybody like 2 more minutes. I know I want you to think, but at the same time, I can't give you like so much time. Okay, so I give you just 2 more minutes, and you have to fast do the next question. But I don't know how to start that. HF and dot. Okay, I think I'll run through it. Okay, I'm going to show you why there's a limitation to this question. Very tricky. This was an A-level question. Okay, very tricky. So HF2 minus, right? Let's take a look. So if you try to draw the, say you try to draw HF2 minus, and you do it this way, right? You try to draw F in the middle. But the funny thing is, you draw a single bond here, right? You draw a single bond here, and you draw a single bond here. So, but there's a minus. So, I don't know how where you're going to put a minus, because 1, 2, 3, 4, 5, 6, 7, right? And then you're going to put a minus on this F. It doesn't make sense because now F we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. So it doesn't, it's wrong because F cannot have more than 10 electrons. And if you try to put a H in the middle, it's also impossible because you try to form a bond here, you try to form a bond here, possible because hydrogen maximum only 2 electrons, right? How can you have 4 electrons? So there's so much limitation. So let's take a look at how this structure was formed. Okay, so this structure was formed this way. So I want you to imagine there's actually HF. Okay, and the minus actually still goes to the more electronegative atom. It went to the F minus. Okay, so then we do this. Delta minus delta plus. You get what I'm trying to say? What are you supposed to draw? What's this in between? What's this in between? Very good. So it doesn't have to affect the number of electrons between them. Okay, very tricky. Have you seen a molecule, an ion with hydrogen bond within it? Very tricky. Okay, so very, very tricky question. All right, there's a hydrogen bond. It fulfills the criteria, right? Hydrogen bond and a covalent bond. So there's hydrogen bond between HF and F minus and a covalent bond. So the hydrogen doesn't have to have more than 2 electrons and the F doesn't have to more than 8 electrons. Are you me? And it fulfills the criteria because again, you can see the H is attached to F and a lone pair on the F. Okay, so this is a hydrogen bond for you. Okay? Yeah, because I saw you writing there. Okay, so there's hydrogen bond and covalent bond within that whole ion. Okay, okay, let's try the next question. Okay, for this question, I want you to think in terms of extensiveness of hydrogen bonds and the strength of hydrogen bond. If I ask you who has a stronger hydrogen bond and who has more extensive hydrogen bond, I want you to think through. Okay, who has more extensive H bonds and which one has a stronger hydrogen bond? If you get that, you can answer this question. Okay, because hydrogen bond, you have 2 kinds of criteria, right? It's either stronger or more extensive. Okay, so think through for a while. Okay, last week we talked about extensiveness of H bonds and we talked about strength of H bonds. So I'm going to apply it. Okay, I'm going to help you with the extensiveness. I think this one, if I look at extensiveness of H bonds, right, it could be a bit tricky. So let me help everybody. Okay, look at ethanol, right? Look at ethanol. If you look at the O and the H, right? O and the H, you notice O has two lone pair and there's one H. So if I like what I mentioned last week, I said if there's 1 million alcohol, right? If there's 1 million alcohol, how many H's would there be? In fact, I mean OH, don't care about other H. OH, there'll be 1 million H, okay? But yet there'll be 2 million lone pair. Okay, see that? Okay, 1 million H, but 2 million lone pair. So who is limiting? The lone pair is in excess, and H is limiting. Can you see that? Right? Yeah, the lone pair is excess, and H is because a hydrogen bond. Remember what I taught you? Hydrogen bond is between a H and a lone pair in a 1-to-1 ratio. Okay, so now you can see from this molecule, there's not enough H, but there's a lot of lone pair. There's 2 million lone pair. So 1 million lone pair will be not used up. So if I try to draw a hydrogen bond, right, I'll probably say, okay, this H, right? Okay, I have to rotate it. Sorry. Okay, so I'll say for this molecule, okay, for this molecule, I'll say that for every H that can form a hydrogen bond, I can only use one lone pair again, because I got two lone pair, but I can use one because the other one is excess. Okay, for this one, if I have 1 million of this molecule, okay, if imagine I have 1 million of this molecule, okay, look at a H attached to N. I'm looking at this 2H. I will have 2 million H's, right? The H I'm talking about is only these 2 H's, okay, but I have only 1 million lone pair, 1 million lone pair. Okay, so which is in excess? You can realize that H is in excess, but lone pair is limiting. Got it now? Lone pair. So for every lone pair that I use to form a hydrogen bond, I actually only can use one hydrogen because the other hydrogen cannot be used. Okay, so my point is this. You realize that the extensiveness for H bonds are the same. Notice extensiveness. So you can see that the hydrogen bond is here and here. Lone pair cannot be used. Hydrogen bond uses lone pair and one H. The other H cannot be used because I got too many H's, right? 2 million H's. Only can use 1 million. So the point is extensiveness is the same. So you can't talk about extensiveness of hydrogen bond. Got it? Okay, so the only thing you can talk about is the strength. So who is stronger? Which hydrogen bond is stronger? Which hydrogen bond is stronger? Jaden? Very good. Okay, yeah. So oxygen is more electronegative. That's it. Okay. O more delta minus, H more delta plus, stronger hydrogen bond. N less delta minus, H less delta plus, weaker hydrogen bond. I mean, so it's all about the strength of the hydrogen bond. Okay. So no need to talk about extensiveness, but I just want to run through with you to check whether the extensiveness is the same or not. Okay, so ethanol has a higher boiling point because oxygen is more electronegative than nitrogen. This causes the OH bond to be more polar. More polar means O is more delta minus, H more delta plus. Okay, N less delta minus, H less delta plus. So resulting in stronger hydrogen bonds in ethanol. Got it? Hence a higher boiling point. All right, so this is about strength of hydrogen bond. Okay. Later, you have one more question to check whether it has more extensive or less extensive, right? So we'll check one more. You see, because this one I more or less helped you. Okay, try the next question. Okay, next was an A-level question. Okay, something to do with H bonds again. Okay, next slide. Okay, A-level question. Just for information, I'm just going to draw for you ammonia. See, every one of you drew hydrazine already. We did draw hydrazine in part 1, chem bonding part 1. So hydrazine looks like this. NH2, then N here, H here, H here. Okay, with a lone pair. Okay, so this hydrazine and there's ammonia. Why does hydrazine have a higher boiling point than ammonia? That's it. Ask yourself, the first question is, because it's boiling point, you're breaking intermolecular. Am I right? They must ask yourself what kind of intermolecular there is, and yeah, and suggest a reason. Now, all along my answers deal with hydrogen bonds. Okay, I'm just telling you that we just finished hydrogen bond, right? I want to say that a lot of the answers here deals with splitting based on H bonds. Okay, let's run through the first one. I'm going to give you some time to think. Okay, is the strength of the hydrogen bond the same? Is the strength of the hydrogen bond the same? Yes or no? Yes, because it's nitrogen, right? Yeah, strength of hydrogen bond is the same. So how about the extensiveness of the H bond? So you realize for this molecule, right? Every time you use a hydrogen bond, right, it's between a lone pair and a H. But this one, lone pair is limiting. So for every lone pair that you use, even though you have 3 H's, you can only use 1 H. Okay? Okay, so that's understanding. So in this case, who is limiting? You have 2 lone pair, but 4 H's, right? 4 H's. So I always say that for every lone pair that they use to form a hydrogen bond, you can only use 1 H. Okay? So because of the ratio, right? For every lone pair that you can use, you can only use 1 H. So if you look at it, look at what I've just drawn, right? So since the strength of the hydrogen bond is the same, but for per molecule, you realize that this one has like 4. But for this one, I can only draw 2, right? So I guess you get the idea that this guy would have more extensive H bonds, which will result result in a higher boiling point. Okay, so this is what you can copy down for the first part. Okay, so I hope you got the idea. Okay, actually another reason you can also give, I'm going to say, but this is suggest a reason. The other reason is I told you all molecules have IDID, right? And IDID is dependent on what? Number of electrons, right? So this guy has more electrons. So even the IDID for this one should be stronger, okay? But I guess that's another reason, but they only want one reason. So I just take it as the hydrogen bond is the more important reasons, right? Okay, so write this down. Both NH3 and N2H4 are held together by H bonds. However, there are more extensive H bonds, right? More extensive H bonds between these molecules due to the greater number of lone pairs and H pairs. Okay, so as more lone pair, more H's, you can form more hydrogen bonds. resulting in a higher boiling point. Okay, so we're actually only talking about the extensiveness, not the strength. Strength is the same because both are nitrogen anyway. Yeah. So when we talk about, when you do hydrogen bond questions, you must always ask, is it the extensiveness or is it the strength? That's why it's a bit more tricky. Okay, so now when you look at this two, is it about the strength of the hydrogen bond or is it the extensiveness? Okay, now you have hydrazine and hydrogen peroxide, right? Okay, look at these two molecules. Ask yourself, is it the strength or is it the extensiveness? Or is it both? That's the next question already. Okay, that's the next question. What's this question? Suggest a reason why the boiling point of H2O2 is significantly higher than that of N2H4, right? So I drew down nicely. Okay, this N2H4, right? And then there's H2O2. Okay, what can you say about extensiveness and the strength? Maybe I just check. Okay, Jeremy, help me out. Jeremy, okay, tell me. Do the extensiveness same or different? Huh? Different. Okay. Over here, who's limiting? H or just write together. H or lone pair limiting? Lone pair. Okay, good. Lone pair. So every lone pair I use, I can use one H. Can? For every lone pair I use, I can use one H because the lone pair and H is always 1-to-1 ratio. Okay, in this question, Jeremy, help me. Who's limiting? H or lone pair? Okay, good. For every H I use, I can use one lone pair. Okay, for every H I use, I can use one lone pair. So what can I say about the extensiveness? Per molecule, it's actually the same. Okay, yeah, it's actually the same. Are you me? So I already told you, right? For every, who's limiting first? For every lone pair I use, I need to use one H. Right? For this one, because H is limiting, for every H I use, I can use one lone pair. So the extensiveness is the same. So I guess you know the answer already. It's not about extensiveness, it's about the strength. So oxygen, again, is more electronegative than nitrogen. Right? This more delta minus, this more delta plus. The hydrogen bond form must be stronger. Okay? This one less delta minus and less delta plus. The hydrogen bond form will be weaker. So say stronger hydrogen bond. I didn't talk about extensiveness. I said now I talk about stronger. So stronger hydrogen bonds between what are H2O2 molecules compared to that between N2H4 molecules. Okay, because same concept, OH bond is more polar than NH bond, as O is more electronegative. Okay, this is very similar to the ethanol question, ethanol and the INI question just now. Can understand? Okay, so that's how it's done. Okay, a bit tricky. That's why I say you have to look at both aspects. Okay, let's do part 3. Okay, part 3 is a bit tricky. Okay, part 3 is definitely a bit tricky, but just read through first. Yeah, I'm gonna help you a bit. I'm gonna give you the answer, but this is how it works. Okay, this is actually acid-base reaction. Ammonia, bubble through this, right? Is actually acid-base reaction. It will form a salt. And salt, how do you know it's going to be a salt? Because they say right crystals like ionic compounds, salts, right? So salts are not very soluble in organic solvent, right? Like oil, you try to dissolve sodium chloride in oil, it's not going to be very soluble because they're very different. Okay, ionic compounds dissolve very well in water, which is polar. Organic solvents are non-polar. Ionic compounds don't dissolve very well in non-polar compounds. Okay, so this actually is a salt. So I'm going to give you an idea and hopefully you can write it. So if you know how to write ammonia plus HCl, right? Okay, you can balance this. I believe you also can balance this. If you can balance that, I believe you can balance this too. Okay, and the products are all ionic compounds. Okay, so you try the top one. If you can write it, you should be able to write the bottom. Okay, and that is your A. Okay, that's your A. Try. I'm giving you a bit of a hint. Okay, if you can write the top one, you surely can write the bottom one. I don't give you answers immediately. I must think. We're going to put ions at the plus and minus. Plus minus good. Okay, just give every 2 minutes, or 3 minutes to finish up this question. Okay, just do 3 minutes to finish up this. You can write like that. You write like that, I don't know what it's. You can write like that. You write like this form. This is like molecular form. I don't use to put all the N and write that separately. What does it look like? If you write like that, I don't know what it's. Okay, what I help you to do is this part, the solution A in water, right? You should know what you wrote here, you should get it. Then yeah, you must tell me what's the gaseous mixture. Right? Some of you have not given me. What's the formula of the particles in the gaseous mixture? It is sublime, moist, red, limits, paper, turn blue. So what's the gaseous mixture? Okay, let's take a look already. I think enough time. Okay, I think the top one is quite well done already because if ammonia plus acid, right, HCl will form salt, right? So the salt is actually I wanted you all to show me ammonium plus Cl minus, okay? Ammonium chloride. Okay. So if you do the same thing over here, this guy will take in the H plus and you form ammonium. I know you all put NH4, NH3, but to be precise, you should put NH4 plus and N3 minus. Okay. So to be precise. So these are crystals. Okay, these are ionic compounds. That's why when you dissolve it in water, it's a good conductor of electricity, right? Because they're aqueous ions. So the solution of A in water, what are the particles? They want the particles. So what's the solution of A in water? The particles would be NH4 plus and N3 minus U. I want you to write it as ions. Got it? So it's soluble in water. Got it? Okay, how about this part here? When solid A sublimes, what is it? Okay, so heating solid A. Okay, heating solid A, right? So you're heating this NH4 plus. Sorry, you're heating this NH4 plus N3 minus. You heat this. Okay, then after that, they say the moist red litmus at held the mouth of the test tube turns blue. Turns blue means is basic. So there must be a basic gas, right? So you know what? Actually, the whole thing is the reaction just reverses. From here, you heat it. Sorry. From here, you go this way, right? But when you heat it, it goes back. So actually, the final answer is when you heat it, it gives you ammonia and HN3. Okay, but why is it basic? It's because of this guy. This is the basic one. So it turns red litmus blue. Is okay? Okay, but you know, realize something. This is basic and this is actually acidic. Okay, just now remember we did it. Acid plus base, right? Base plus acid. Okay, so this is actually acidic. Okay, so somebody tell me why. Okay, so can somebody tell me why you saw the blue color? You saw it turn blue, but you didn't see it turn red, even though this is acidic gas. Okay, why? Can somebody tell me why you saw the blue, but you didn't see the red? Any idea? Why do you see blue first? Actually, I should say you see blue first. Why do you see blue but not red? Even though this is acidic gas, right? But why not? Anybody? Okay, the answer is, who is lighter? Who is lighter? Who is lighter? Ammonia or HN3? Ammonia, right? Yes. So because ammonia is lighter, the gas will come out first. Okay, the one that comes out first will be the lighter gas. So you will definitely test for ammonia first before you can test for any acid. Okay, so very tricky. That's the answer. So this one, the ions and the sample, the gaseous mixture is basically they just want ammonia. Okay, to show me that it's actually basic. So that's all. Okay, so when A sublimes, they just want to say you can detect ammonia. That's why it's the base. These are the ions in solution. Got it? Okay, so very tricky. I'm trying to say these questions are kind of tricky, but they're all A-level questions. Okay, yeah, a bit tricky. Okay, so when you heat it, actually the reaction just reverses. Got it? Okay, let's move on to the next part. Then we continue. Just one slide for concepts. Okay, everybody good? Okay, so it was actually like that, ammonia plus, and actually it reverses. Okay, could actually reverse. Okay, when you heat it, it goes back. All right. Okay, so let's move on. Okay, so let's run through the next part. Okay, let's look at this part. We're going to compare strength of the three types of intermolecular force of attraction. So very quickly, let's look at them. Okay, so maybe just take note of this. If the number of electrons between the different molecules are similar, right? So this is why we compare molecules of the same size, right? The number of electrons are, if the number of electrons between different molecules is similar. Similar means they are the same size. You must take note, hydrogen bonds are stronger than PD-PD, and PD-PD is stronger than H bond, than ID-ID. Okay, so H bond technically is the strongest, followed by PD-PD, then followed by ID-ID. Okay, so it works this way. But provided you are comparing molecules of the same size, right? So you can see for these three, we're comparing molecules of the same size, right? They're comparing molecules of the same size. So propane being just a hydrocarbon is a non-polar. Okay, so non-polar means it only has ID-ID. Okay, dimethyl ether. I went through with this last week. Everybody, if I try to draw it one more time, dimethyl ether looks like this. CH3O, CH3 is a band about oxygen. And then I showed you that the dipole moments don't cancel out. You see that? They don't cancel out. There's a net dipole moment pointing this way, up. Okay, so this molecule is polar. So polar will have PD-PD and ID-ID. Right? Okay, then this one is pretty obvious because you see a H attached to O. This means that it has hydrogen bond. Okay, so you see a H attached to O, you know that this compound will have hydrogen bond. So it probably will look like this. The H, right, will form a hydrogen bond to the O here. Okay, so this is so this one is a hydrogen bond. Okay, so I put hydrogen bond. Okay, so very simple. Okay, so you can fill in all the gaps here. Propane is non-polar, so only is ID-ID. Dimethyl is polar, so it's ID-ID and PD-PD. And ethanol has H bond. So you can see from here, you can see that this has the lowest boiling point because it only has ID-ID. Then the one that has the next highest boiling point is is what? Dimethyl ether, because it has PD, ID. And look at the one with hydrogen bond is 70, the boiling point is 70. It means hydrogen bond is the strongest. Can you see that? So the ranking goes this way. Can you see that? Yeah. So the one, the lowest boiling point is the one with only ID. Okay, and then this one has extra PD. This one has extra PD, higher boiling point. This one has hydrogen bond, highest boiling point. Okay. Okay, let's answer the last question here. Okay, explain why iodine has a higher boiling point than water. Okay, why iodine have a higher boiling point than water? Okay, number one. Okay, okay, maybe I should ask this question. So iodine, right? Iodine and water, right? Okay, iodine actually is if you think about it, right? Iodine actually is a crystalline solid at room temperature. Okay, just ignore that first. Iodine is actually, you can find it in a crystalline solid, and water is a liquid. Okay, so so over here, iodine has what kind of intermolecular? Michelle, iodine has what kind of intermolecular? Iodine is a polar or non-polar molecule? Very good, non-polar. So non-polar means it has what? Non-polar means it has. Very good. Okay, water has what kind of not done? Water has what kind of intermolecular? Water has what kind of intermolecular forces of attraction? ID, PD, or H bond? Very good, because the H is attached to O, right? This one is H bond. Okay, can you tell me now which one is stronger? H bond or ID stronger in this case? Which one stronger? H bond stronger? But if I'm going to tell you that iodine is a solid room temperature and this is a liquid, which intermolecular is stronger? Very good. This case, listen, this case ID is stronger. Then you must be thinking, hey, how come ID stronger, right? I just contradict myself. I told you hydrogen bond stronger, right? So why is this one ID is stronger? ID can be stronger, but why is ID stronger? So ID is dependent on what? The size. Very good. The number of electrons. You know, iodine has how many electrons? Let me count. Iodine has 106 electrons. And water has, oxygen is 8, right? I think oxygen is 8, right? 8 plus 2, right? So do you notice that iodine has 10 times more electrons than water? So 10 times more means the ID is so much stronger already. Outweighs the hydrogen bond. So don't think ID can never be stronger than hydrogen bond. It can for a very big molecule. Okay, so over here, the strength of the ID depends on what? Number of electrons. Okay, so iodine has many more electrons as I just calculated for you, right? So the ID is stronger. Okay, so in this case, ID is significantly stronger than the H bonds. So do not think H bonds always must be stronger. So a molecule with a lot of electrons, the ID can be stronger. Can? So it's all in the context of the question, right? Okay, with that, I think you can do some questions with it. So this is a very important concept, okay? So ID, just trying to show you that ID can be stronger than H bonds, provided the molecule has a lot more electrons, okay? Okay, so can you try the next question? Yeah, I think it's next one you can do it. Okay, let's try. It's all comparing boiling point. You have to ask yourself what kind of intermolecular, all these, you must ask yourself what kind of intermolecular forces of attraction are there, and then explain accordingly. You only did booklet ask from me, otherwise you look at the wall, you have all the MR. Okay? You look at the wall, you get the MR. Okay, this is CO2 and this is SO2. Okay. So firstly, you know that this shape is linear, the dipole moments cancel out. This is non-polar. This one, the dipole moments don't cancel out, they don't cancel out. So this one is polar, and I hope you can continue to answer the question. Okay. So polar has what kind of intermolecular, non-polar has what kind of intermolecular. And okay, do two slides, this one and next slide. Okay, 2 to 3 more minutes. I'll do this slide. You should then move on to the next slide. Okay, for 3 more minutes. Okay, let's look at the question ready for this one. Okay, let's take a look at what you're writing. Okay, very good. Non-polar, polar, right? So this guy has only ID. Okay, by this polar, it has both ID, it has both ID and PD. So you must at least mention that. Okay, so very quickly, let's do the first part. SO2 is a polar molecule. Keywords, I'm just going to highlight keywords. SO2 is a polar molecule, right? SO2 is polar, while CO2 is non-polar. Okay, so that's important. So SO2, there is PD and ID between SO2, and there's only ID compared to just ID in CO2. Okay, must write all this up. Then, okay, so that's actually good enough. So you can see that SO2 has PD on top of the ID. Okay, but at the same time, you can write a little bit more, but if you didn't write this, I think we're still okay with it. So, so SO2 has higher boiling point because of additional PD. All right. But at the same time, whose ID is stronger? At the same time, you notice SO2 has slightly more electrons. I think so. Yeah. Sulfur is the next period. So SO2 has more electrons. See, this is the next part. SO2 has more electrons than CO2. That implies that SO2 has a greater ID. So this is additional. Okay, you can write this down. I think this is probably additional. Okay. So because we know that ID is also dependent on number of electrons. The one that has more electrons will have stronger ID. Okay, so this is additional. Okay, how about this one? This is definitely a bit tricky. Why I say this question is a bit tricky? Because SO2 is polar and SO3 is non-polar. Okay, SO3 is non-polar. And it only has ID. Okay, so why is it then SO3 has a higher boiling point? So the only thing you can say is why SO3 has a higher boiling point, because SO3 has, okay, it means that the ID here must be stronger than these two add together. Okay, and why is it possible? Because SO3 has more electrons. Okay, because ID is about electrons. So just say, although SO2 is polar and SO3 is non-polar, okay, one is polar, one non-polar. Okay, the answer is here. Because SO3 has a higher boiling point. Why? Because SO3 has more electrons. So it's actually the last part here. SO3 has what? More electrons. So it has more electrons, and the strength of the ID outweighs the PD and ID of SO2. Okay, you answer based on the data. Are you with me? The data will tell you SO3 has a higher boiling point. Then this is the best logical reason you can give. More electrons, stronger ID, and this ID outweighs the ID and PD over here. Got it? Okay? So this one is a bit tricky. Because SO3 is non-polar, but yet higher boiling point, right? So why? So this is the only logical reason you can give. So this one is still considered tricky. So you always have to answer your question based on the data given. If they never tell you, SO2 is higher boiling point, I think I will write down SO2. If they didn't say this, highly likely that I write SO2 as a higher boiling point. Okay? Yeah, more likely than not. Okay, but since they told me SO3 is a higher boiling point, answer according to the question. Okay, this is quite well done. Actually, the learning point is only for part B. Okay, it's basically just part B. That's the learning point. Okay, what I highlight means that's my marking point. Okay, among all these four, right? Why does HF have the highest boiling point? If you look at the graph here, it shows there's a bump. All right, there's a bump up here. So HF should be right at the bottom here. Technically, HF should be over here, but it wasn't here. Okay, it was up here. All right. So they say, why does HF have the highest boiling point? They say because HF has hydrogen bonds. Highest boiling point. Just if I see the word hydrogen bonds, I'm okay. Okay, but now this part I want to talk about. Why is the boiling point increasing? Why does the boiling point increases from HF to HBr, HCl to HBr to HI? So I want you to write this down. HCl, HBr, and HI. Okay, write this down. Huh? So all of them are non-polar, all of them are polar. So all of them have ID, and PD. Okay, but if I'm going to ask you this question, which one has the strongest ID? Out of these three, right? Which one has the strongest ID? Definitely is the one with more electrons. So you can write down HI has the strongest ID. Okay, and HI. But for PD, who's the strongest? Who do you think PD is the strongest? Ellie? PD, which one's strongest? The one that's most polar, strongest PD. So which one is it? Good. Okay, HCl. You can see Cl is Cl, very delta minus, very delta plus. That's delta minus, that's delta plus. Okay, so if I tell you strongest as PD, it's actually HCl. Okay, so since you know that the boiling point goes up this way, right? Which one plays the bigger role here? ID or PD plays a bigger role. Since the boiling point goes up from HCl to HBr to HI, who plays a bigger role? Okay. PD strongest for this one, this one's strongest PD. This one HI strongest ID. But out of all the boiling point, right, HI is stronger, highest boiling point, right? So who plays a bigger role? Very good, ID. So your answer is just ID. Okay. So just say from HCl to HI, the boiling point increases due to increasing strength of ID. Okay, don't even have to talk about the PD. Just say increasing strength of ID because ID is the one that plays a bigger role here. Can? Okay, so increasing strength ID as correlates with the number of electrons. So HI has more electrons, ID stronger, higher boiling point. Is okay? So you need to know, at least take note, the more polar the molecule, the stronger the PDP. Okay, but in this case, ID wins. Okay, let's do one more slide and I'll teach you the next concept. MCQ, so it should be quite fast. Yeah, you need just 2 minutes, I'll run through. Okay, those at home, can you just type in the chat? I want to see your answer for these two MCQ. Okay, 30 more seconds. Okay, Cadence and Sienny, just type in the chat, your answer. Okay, let's go through. I think most of you are more or less done. Okay, let's try the first one. The strength of the PD-PD interaction increases in the order. Okay, this is not possible, right? HCl is PD-PD. Actually, ammonia is hydrogen bond. It also has PD-PD because it's still polar. So actually, the truth is the hydrogen bond is a strong form of PD-PD. Again, the hydrogen bond is actually a very strong form of PD-PD. So this guy would also have PD-PD. Okay, but I say this PDP is actually the terms of hydrogen bond. Okay, but CO2 is non-polar. So it actually doesn't even have PD-PD, right? Yeah, it's non-polar. So it only has ID-ID. So of course, A is wrong already. Okay. And over here, they still mention oxygen, carbon dioxide, and talk about PD-PD, but carbon dioxide is non-polar. Okay, carbon dioxide is non-polar. It doesn't have any PD-PD. That's why B is also wrong. Okay, I'm not sure why they keep talking about PD-PD for carbon dioxide, because it doesn't have any PD-PD. Okay, because it's a non-polar molecule. Okay, for this one, if you have to do some calculation, it's like a HCl, right? So you're thinking about ID is dependent on number of electrons. So ammonia has 10 electrons, and CO2 has 6 plus 16, 22 electrons. So it failed already, right? So HCl is 17 plus 1, 18 electrons. So it doesn't work. Okay. So ID is dependent on number of electrons. So in fact, I would say that CO2 would have be on the right hand side. Okay, yeah. So look at number of electrons. Okay, so this out also. All right. So answer definitely is D. So ammonia has a higher boiling point because it has hydrogen bond, and the hydrogen bond is stronger than the PD-PD. Okay, so this is logical. Okay, ammonia is hydrogen bond. Okay, for the next one, if you've done it, the answer is, let me see, answer is C. Okay, so why this one doesn't have a hydrogen bond? Because it looks like that. This ammonium, okay, this ammonium. Okay, so there's a H attached to the N, but there's no lone pair on there's no lone pair on F, O, or N. Okay, so this one cannot have hydrogen bond. Okay, how about the next two? This one here, I think we know. Okay, this one you can try to draw it out so you can see there's hydrogen bond. Okay, HNO3 looks like this. You can draw it out. Okay, if you didn't know how to draw it out, better draw it out. So this is HNO3. Okay, so this is HNO3. The H is attached to O. If I have to draw it out, another molecule. So I guess it should show you that there's hydrogen bond. There's a dative bond, a double bond, and yeah, it's like that. Okay, so the lone pair here, easily this one can form H bond. Okay, so yeah, so this is 2 and 3. Very good. Okay, this two have, but not for the first one. Okay, the first one don't have any O, F, or N with a lone pair. Okay, yeah, so not possible. Okay, C, yeah. Okay, let's look at water and ice. Okay, we're going to talk about water and ice. Okay, what happens when water become ice? Okay, and we're going to learn why ice floats on water. Okay, so let's take a look. Okay, let's take a look at this. So this is C. Okay, okay, this one I was going to skip, nothing much, but let's just read through. Okay, let's see the structure of ice. The structure of ice. Okay, if you look at water, you look at Okay, so I'm going to show you what ice looks like. Okay, and look at this. Snowflake looks like this. I'm going to show you why it can look like this. Okay, if you look at water, right? Water is this. Okay, water is this. So if I just say pure water, water has a two lone pair and two bond pair. The shape is bent and the angle is 104.5. Okay? Okay, so now if you form ice, what really happens? If you form ice, right, this is exactly what happens. Okay, when you form ice, water comes very, 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 very close to each other. Okay, very, very close. So I'm going to draw it very, very close to each other. Okay, because it's ice, right? So this is what happens when you form ice. Okay, when you form ice, this is what happens. The hydrogen and the O will form very strong hydrogen bond because it's very close. Okay, very close. Because it's very close, it will form very strong hydrogen bonds with another water molecule. Okay, so now if you look at about O, right? Look at about O, there are two very strong hydrogen bonds and there are two covalent bonds. So you know what? How do I write about O? So I say about O, right? Then look at it about O, right? No, about O now, it actually has, listen, it has actually 4 bond pairs. Okay, but I'm going to put the word, I'll put a bracket bond pairs. Actually, this 4 bond pairs is actually considered as 2 bond pair and 2 hydrogen bonds. Okay, but this hydrogen bond is almost like a bond pair already. Are you me? This is H bond, huh? Because this is a bond pair. Can I say this is a bond pair? But the hydrogen bond is so strong, it functions like a bond pair. So what is the shape of oxygen? If I tell you there are 4 bond pairs, we say the shape now has changed to what? No space to write. Okay, has changed to tetrahedral. Okay, because now instead of like 2 bond pairs, 2 lone pairs, it's like 4 bond pairs, right? So the shape is almost like tetrahedral, and I'm going to draw what happens to the angle. The angle become 109.5 because I use the word tetrahedral. So you know what? When it becomes ice, right? You realize something, huh? When it becomes ice, what happens to the angle? Okay, what happens to the angle? From water 104.5, now when it becomes ice, is 109.5. So when it becomes ice, what happens to the angle? The angle opens up. So we call it, it has an open structure. So if you think about it, what is density? Density is actually mass over volume, right? So when it becomes ice, what happens to the volume? Because when it becomes ice, the angle becomes bigger. So it opens up. You see, the angle opens up, right? So when it opens up, the volume increase. Okay, the volume increase. So when the volume increase, what happens to density? Density will decrease. So actually, when ice forms, it's about the angle. Okay, the angle opens up from 104.5 all the way to 109.5. Okay, so because hydrogen bonding, it gives rise to an open structure in ice. Okay, so yeah, that's how it works. Okay, so open structure, the angles open up, the volume increase, and the density drop. That's why ice will float on water. Okay, so this is the idea. Okay, if you have this concept, you should be able to do this question. Okay, so you notice, look at snowflake. You realize something about snowflake, right? Look here. I mean, that's how you draw snowflake, right? I told you, right? Oxygen has what shape? Tetrahedral. Do you realize snowflake? This O here has a tetrahedral structure. You realize? Tetrahedral? You see that? All these are oxygen, you know. You realize these are oxygen? And they all like have how many bond pairs? 1, 2, 3, 4. There's ice for you. Okay, snowflake. Very interesting, right? Yeah. Okay. All right, so let's try the next question, see whether you can do it. Okay, it has something to do with ice. Yeah, it's actually everything I mentioned to you. You have to write the names. So 105 technically is a 2 bond pair, 2 lone pair, right? But if it's 109.5, it's like 4 bond pairs. So you see, draw, yeah, so I guess that's my, the thing I answer, okay? Why a water molecule is bond angle is 105 and not 109.5? You must apply your VSEPR theory to explain the smaller bond angle. Some key points. Okay, 2 minutes, that's all. Okay, let's see how we answer a question like this. Okay, why there's a key point you have to talk about, right? Why is it 105 and why is it not 104.5? So this is you apply your VSEPR theory that lone pairs repel more than bond pairs. Can? So let's see how you write it. Lone pair repulsion is greater than lone pair, greater than bond pair. So when you have I think you remember what I mentioned, that if there's lone pair, right? So lone pair, they repel more. You push the bond angles closer. Okay, so you must have this in your answer key, right? Okay, this is the main thing. Lone pair repulsion greater than lone pair, greater than bond pair. So it'll push the bond angles even closer, and then the angle will be lesser than 109.5. It'll be like 105. Okay, so I mentioned that the two bond pairs are pushed closer together, resulting in a band angle that is less than 109. It's okay. So that's the criteria that we are looking at. Okay, this is a VSEPR second principle. All right. And after that, they ask you why the bond angles in ice are 109. So 109, you must treat it as there are 4 bond pairs. Okay. Then you must say, but these 4 bond pairs are due to 2 bond pairs and 2 H bonds. But the H bonds are already considered bond pairs because they are very strong. Okay. So if you can tell, you can write something along those lines. You can explain why it's 109. Okay, so I'm just going to show you. So the 2 lone pairs on oxygen is hydrogen bonded to 2 other water molecules. Okay, they're talking about these 2. So you'll say there are 4 bonds. Okay, but I think I put a bracket here. Okay, because it's not really 4 bond pairs. The bonds are the bond pairs and the hydrogen bonds. So there are 4 bonds around each oxygen. So the arrangement is tetrahedral, which accounts for that bond angle is 109. Okay? So these 4 bonds are, you know, 2 bond pairs and 2 H bond. Are you me? Okay, so it's something along the line of having 4 bond pairs. Okay, but that can only happen for ice, because the H bonds are very strong as the molecules are much closer. Okay. Okay, the next few questions gonna make you write a lot. Okay, but the no choice. The next few questions are A-level questions, and yeah, I'm gonna make you write a lot. So I'll just go through with you. I'm not gonna wait for you to do it. But you must learn to write the way you're expected to write. Okay, I tell you why later. Okay, everybody copy this. Okay, the next few questions you're gonna write quite a fair bit, so be prepared. Okay, so let's take a look. I'll do with you. Okay, then you will copy down after I explain. You just copy down the answer. All right. So make sure if they come out something like that, you can write something similar to what they're asking. Okay, very good. Okay, let's look at it. So A-level recently, I think since 2019, they've been coming a lot of questions on chem bonding, asking about comparing boiling point, right? Whether it's organic compounds or not. Okay, so let's take a look. Okay, look at this. This 216. Okay, explain the following comparisons in terms of types of intermolecular and how they arise. Okay, so this is the part that stumps students. They say not just telling me the intermolecular, but how they arise, right? Then they say use diagrams where appropriate to illustrate your answer. Okay, 6 months, quite a lot. Okay, let's take a look. The boiling point of ethane is higher than that of methane, right? So I guess if you understand the simple concept that these two are non-polar. Okay, we just go through the basic concept first. All hydrocarbons are non-polar. Okay, so both of them have ID-ID. Okay, non-polar means they have ID-ID. Then you ask yourself, ID-ID is dependent on number of electrons, right? So the one that more electrons will have stronger ID-ID. So this guy has more electrons. Okay, so the ID-ID here must be stronger than this one. Okay, so it results in a higher boiling point. Okay, but the tricky part is not about this. The tricky part is how they arise. So you have to write down how ID-ID came about. Okay, how ID-ID came about. So just follow through and copy down. I need to copy, no worries. Okay, so this is the part, the how they arise. Okay, I need you to learn how to explain how they arise. Right? So they are both non-polar. Okay, so the how they arise is actually from here starting. Electrons are always constantly moving. All right. Electrons are always constantly moving. So I told you must copy a lot. So ID happens when electrons are always moving, and it could actually end up on one side. It'd be lopsided, like delta minus, delta plus. That's called instantaneous dipole. Okay, so the electron density of molecule can be unsymmetrical. It can go to one side, unsymmetrical. So resulting in instantaneous dipole. Okay, resulting in instantaneous dipole, and this will induce another neighboring molecule. So this part is the one that students couldn't write because they don't know how to describe how ID arises. Okay, which induces a short-lived dipole. So induces a short-lived dipole. That's your induced dipole. Okay. Okay. So did you copy it? Did you copy? Oh, it's there, right? Oh, sorry. Close passage. Sorry. Oh, sorry. So you just have to fill in the blanks. Okay. Yeah, only sorry. I thought, okay, the next question must copy down. I think this one I gave you all some things to fill in. Okay, just fill it. Okay, so ID becomes stronger when electron cloud increases. This one we know. So ID is becomes stronger when there's more electrons. Okay, more electrons means electron cloud more easily distorted. So then say ethane has a larger molecule with larger electron cloud, more electrons. Okay, so stronger ID, more energy is needed to overcome it. Okay, so fill it in. Yeah, I don't remember. I let you fill in the blanks. Okay, but I know the tricky part is this part, the how they arise. So you must learn how to explain also. Okay, it was an A-level question. So then I think the subsequent years they ask how PD arise. Then subsequent years ask how hydrogen bond arise. Okay, so we must at least learn a bit. Okay, fill in the blanks. I think this one most of you know lah, because IDID is dependent on strength, size of electron count. That one everybody gets it. So some of the years, I think at some of the A-level questions, they expect students to write a lot, but the marks a bit stingy. Okay, the marks is a bit stingy. Very good. Okay. Actually, the learning point is you must explain how IDID come about. Okay, let's look at the next part. The other one. Okay. Also you can fill in the blanks. I think it shouldn't be that difficult. The boiling point, I'll come back to the slide. The boiling point of methanol is higher than that of ethane. Okay, so this is pretty obvious, right? This is pretty obvious. Because methanol actually has H attached to the O. So I guess if you can see that, you probably know that methanol already has hydrogen bonds. Okay? Yeah, but ethane is just C2H6. So C2H6 and C2H6 is just IDID. Okay, so I think that's about it. So you can just copy down. Methanol consists OH group. All right. So this is, I think you're trying to explain how hydrogen bonds arises. Okay. So this part here is showing you how H bonds arises. Methanol has an OH group. Since O is highly electronegative, it attracts the bonding electrons. So the H is partially positive. So this is explain how hydrogen bond arises. Okay, so just show that there's a delta plus and a delta minus. Okay. And after that, this is part. Since H does not have an inner shell, electrons, its proton is exposed and interacts strongly with a lone pair of electrons on O in a nearby methanol molecule. So what it means is this. Maybe I just write up in case some of you don't see it. Okay, this is oxygen and this is hydrogen. So when hydrogen forms a covalent bond over here, okay, so the nucleus of hydrogen is over here and is totally exposed, right? I think I mentioned last week that hydrogen here, there is no electrons. Okay, here I highlighted no electrons. Okay, so the lone pair of oxygen, okay, the lone pair oxygen like this one, O dot H, right? The lone pair oxygen here can interact directly with the nucleus. Can you see that? So its proton exposed and interacts strongly with the lone pair of oxygen, electrons of oxygen in a nearby methanol molecule. Can you see that? The lone pair interacts directly with the nucleus. Got it? Yeah? Remember I mentioned this, so it can interact directly with the nucleus. So this is a very, very strong interaction. Okay, the proton is exposed. Okay? Then then after that, just mention H bonds is stronger than IDID. Okay, interaction between partially positive give rise to hydrogen bond. Okay, so this is explaining how hydrogen bond arises. The interaction between the partially positive hydrogen, which is this, delta plus, delta minus, right? The partial H with the lone pair on the O. So this is the H bond. Okay, so take these like model answers to help you explain how H bond arises, how IDID arises. It's okay? Okay? Yeah, no choice. I mean, it's a lot of writing, but I mean, that's the only way to explain it. Okay, let's look at next part. Okay, two more I'll do with you. So it'll be a bit faster. But I think the next one they're asking about how PD arises. So you also have to explain. You ready done? Okay, let's take a look. Okay, next one. Okay, let's see this one. Okay, 2019, right? They say the below tables list the boiling points of some compounds. Suggest reasons for the difference in boiling point between these two. Okay, so yeah, so let's try. Okay, maybe I should ask some of you. Okay, Dylan. Okay, help me out. This molecule is what kind of intermolecular? Dylan? Okay, this one is what kind of intermolecular? We discussed together. What kind of intermolecular does this molecule have? Very good. This molecule is just polar. Okay, dipole most will cancel out polar. So it only has PD, PD, and ID. Okay. Okay, how about this molecule, Dylan? This one has what kind of intermolecular? This one has that? Yeah, very good. Okay, okay. There's a H attached to O, right? So this one has hydrogen bond. Okay. So I guess you should know the answer. Suggest a reason. So look at the boiling point for these two, -24 and 78. So this one much higher, right? Much higher. So it has hydrogen bond. Okay, so just write accordingly. Okay, more energy is required to overcome the stronger H bonds. H bonds. Okay, between alcohol, then the PD. Right, and ID between ether, so higher boiling point. Okay. So more energy is required to overcome the stronger H bonds. So one has H bonds, one has PD, and ID for being polar. I hope you just know that this one doesn't have hydrogen bonds, because this one, none of the H's is attached to a O, right? All these H's are not attached to O, so this one no H bonds. Okay, so the idea when you see H bond, H must be attached to FON. Okay, it's not attached, then no H bonds really. Okay, so that's the first thing you look at. Okay, I hope you realize when I draw like that, maybe you all must see very clearly. It's H attached to the C, okay? It's not attached to the O. Okay, the H is attached to C and not O. Okay. Okay, Amanda, tell me. For you, you help me out for this one. Between these two, okay, which one has higher boiling point? Let's take a look. Which one has higher boiling point between these two? Okay. Between these two, oh, this one is higher boiling point. Okay, 37. So let me just draw it out. Okay, I'll come back to the side if you need to copy anything. Okay, let me just draw it out. How does this look like? It's CH3 S CH3. Okay, this is what it looks like. Oh yeah, this is over here drawn nicely for you. Okay, good. Okay, so okay, but they mentioned that between these two, this one has a higher boiling point compared to this. Okay, so I'm gonna just do something over here. So Amanda, I guess you know that both are polar, right? Okay, both are polar. So over here, I'm gonna say since both are polar, I'll just draw like that. Since both are polar, they would have they both would have ID, and PD. Okay, so who has a stronger ID? One or two, I call it, okay, I call this one, I call this two. Okay, which one has a stronger ID? Good, because sulfur, more electrons than O, right? Okay, I put stronger. Okay, how about the next one? Who has greater PD? PD is about who is more polar. Okay, who is more electronegative? O or sulfur? O more delta minus, right? Yeah, and let's so if I draw a dipole moment, I draw like longer dipole moment, and this one I draw like slightly shorter. So the one that's more polar, I call this polar, but this is more polar. Got it? So in terms of PD, who's stronger now? This one is stronger. Is it okay? Because more polar means stronger PD. Okay. Then which is the bigger answer? Which one wins? You explain in terms of ID of PD. Since this guy has a higher boiling point. This one has a higher boiling point. So are you going to answer based on PD or ID? This one has a higher boiling point. Higher boiling point. This one has higher boiling point. So which one? How to answer? Are you going to answer based? Because this one higher boiling point, this one lower boiling point, right? So you should answer based on what? This one has a higher boiling point because it has a what? Because it has stronger ID. Can't explain in terms of PD. Can? So this one explain based on ID. Can? Right. So that's how you have to analyze it. Due to the larger and more polarizable electron cloud. Because I'm talking about ID already. Can? If you talk about PD, it's off tangent already. Are you me? Wait, everybody understand what I'm doing now? You understand what I'm doing? Okay, you can see that this guy has a higher boiling point, right? So then this guy is because of this, the stronger IDID. Okay. Okay, so due to larger and more polarizable electron cloud, is essentially is like due to this guy has more electrons, the IDID is stronger. Okay. Okay, so if your answer is just all about IDID being stronger, that's how you're gonna get your marks. Is it okay now? Yeah, so the questions are all yeah, it may not be the same, okay? They all tend to be, you have to use the data to explain. Okay, use data to explain. Okay, then you answer the last part. I hope you can do the part 2 yourself, everybody. Part 2, you all should be able to answer. Okay, Jia, maybe you help me out for this one. Can I come back this slide, if you need to copy anything. Okay, why do you think they have similar boiling point for these two? Why? What do you think they have similar boiling point? Well, this is suggest reasons for the similarity. Okay, just give me one. Okay, why do you think they have similar boiling point? Yeah, good. Okay, so that's the same thing. Yeah, same number of electrons. So IDID is similar. That's one reason. Okay, both are polar and a similar electron cloud size, resulting in similar strengths of IDID. Right, similar electron cloud size and similar strength in IDID, and hence they have similar boiling points. Okay, so yeah, pretty straightforward. Okay, let's look at the next one. One more, and then we can move on. But I still have to go through all this because these are like a lot of these are the kind of questions that always students can ask me how to do. Okay, but I'm trying to make sure you all have a feel of it. Okay, and all these are past A-level questions, quite recent. Okay, very good. Similar electron cloud size, similar strengths of IDID, similar boiling points. Okay, the MR is the same, right? So when I revise up, please revise all these parts as well. Okay, for chem bonding, students always have problem answering when compare boiling point or later compare solubility, which is the next part. Okay, compare solubility also. They usually struggle in this too. Okay, next one. You want still copying? Okay, you all can read through this question. You'll see whether you can do it before I ask you guys. And ready? Okay, let's look at next one. Okay, this one I'll still do with you all. Then the subsequent one you'll do yourself. Yeah, I mean after I go through this concept. Okay. Okay, wow, so much to write. Okay, what is meant by the term electronegativity? This is just definition. Please copy down. Okay, electronegativity is the relative ability of an atom in a molecule to attract bonding electrons towards itself. Okay, so anything that's more electronegative will probably attract electrons closer to itself. Okay, so just copy down. There's a definition. It's a relative ability for an atom in a molecule to attract bonding electrons towards itself. Okay, like what I mentioned. So Cl more electronegative than H, electrons are closer towards the Cl. Okay, let's do the next question. I'll come back, don't worry. Okay, predict all possible intermolecular forces which would exist between phosgene molecules. Explain how these forces arise again. My goodness. Okay, so what is phosgene? It looks like this. Okay, so try to draw it out. It's like C double bond O, Cl here. Okay, so all the possible intermolecular force, okay, of attraction, which could exist, right? So this molecule, is it polar or non-polar? Tell me, polar or non-polar? Asha, polar or non-polar? Non-polar. Okay, this trigonal planar, but I draw the dipole moments here. O is more electronegative. I draw it very strongly up. Then I draw slightly shorter. Yeah, there's still a net dipole moment pointing upwards. Okay, there's a net dipole upwards because oxygen is still more electronegative than the Cl. So this molecule is polar. Right? They say predict all possible intermolecular force. So you must tell me this molecule has PD and what? ID. Okay, and that's it. Okay, predict. So they have PD, ID, and then you must exist how they arise. Okay, I think we will skip the ID. Okay, we just write the PD. Because just like I made you write ID already. Okay, we're going to just write for PD. Okay, so let me see here. Okay, don't need to write this one because this one I made you write just now. Okay, how ID is formed. Okay, but I want you to write how PD is formed now. Okay, how PD is formed. This one we write, you can just get from just now. Okay, it's the same concept. Okay, how did PD is formed? You must say the molecule is polar with permanent dipoles, right? Permanent dipoles, write it down. So this is a phosgene molecule is polar. It's a permanent dipole. Means if you look at the entire molecule, if you realize just now what I drew, right? I drew this way. It has a net dipole moment pointing this way. So what it means is if you look at this entire molecule, since there's a net dipole moment pointing upwards, it means that this part of the molecule is slightly delta minus, and this part of the molecule is delta plus. And this is what we call the PD, the permanent dipole. Are you me? Because of the net dipole pointing upwards. So PD interaction arise due to the electrostatic attraction between the delta plus end of one and the delta minus of the other. That's it. So if you want to draw, put a picture to it, it look something like this. Okay, so this part is delta minus, this part is delta plus because of the net dipole. So the interaction between the delta plus and the delta minus here will be your PD. Everybody understand? Okay, so this is how you can write this down as how they arise. Okay, don't write the ID because the one I did with you already. Okay, just make sure you can write all of them. So I think this part is quite comprehensive because it goes through every single one already. ID, PD, and H bond. Okay. So due to the electrostatic attraction between the delta plus of one end and the delta minus end of the other molecule. Got it? Okay, now we go back to some common questions on hydrogen bond. Okay, some other additional questions on hydrogen bond. This one don't waste time copying because I'm not going to give you time to copy it. This one you can rephrase it yourself a little bit from just now. This is also quite recent, right? This is this year, 2000. Okay, this is 2018. Okay, 2018 A level. right, great. Then, okay, so let's run through another two more concepts for H bonding, right? Let's see what is required of you. Okay, let's look at this question. Okay, I want to show you something about this molecule. So ethanoic acid is this. Okay, so ethanoic acid looks like this. So I need some space. So this ethanoic acid, CH3 COOH. Okay, so you notice the way I drew it. Okay, if you look at how I drew it. This carbon is trigonal planar. Notice I drew trigonal planar. Then this oxygen is bent. So I'm drawing bent also. Okay, I try to draw the proper shape. Okay, what did they say? What did they say? They say the molar mass of ethanoic acid is 60, but the molar mass of the gaseous form is found to be 120. So in the gaseous form, once this evaporates, the molecules can come close to each other again. And this is what happens. I'm just going to draw for you again. So this part is trigonal planar. So you have to draw like this. Then this is bent. So it's OH here. You see, it's quite nicely drawn. So you realize that this O can form a hydrogen bond here. And this O can also form a hydrogen bond over here. You can say this delta plus, delta minus. This delta plus, delta minus. Okay. So when the two of them come together with the formation of H bonds between them, we call this a dimer. Okay, the word is dimer. Okay, learn the word dimer. So this is a dimer. Okay, so now the MR is not 60, but it's double of it. That's why the MR is 120. It's okay, it's doubling. Okay, so you hopefully everybody later on can draw this. Okay, the next part. Okay, however, in aqueous solution, they say, however, if you put this in water, no dimerization can occur. Okay, why you cannot dimerize when you put in water? Because once you put in water, okay, there is interference from the water. So interference from water, some of the water molecules will want to form hydrogen bond with this O. So some of the water molecules will want to form a hydrogen bond with this H. Can you see that? So when water interferes, it doesn't allow this molecule to dimerize anymore. Got it? Yeah. So no dimerization can occur in the presence of water. Okay, so let's take a look at a few more examples, right? So these are hydrogen bonds with water. Hopefully you can see here. H bonds with water, H bonds with water. So, okay, last part here. Okay, I want you to take note for A level, right? There are a few dimers that you need to learn by heart. Okay, what other molecules can form dimer? Two molecules combined to give you one. Okay, for A level, write this down. We learned this before. NO2, I mentioned NO2, two of it will combine to form N2O4, which is considered a dimer. Okay, so N2O4 is like this. So this NO2, if you remember, this NO2, and another NO2 will combine with it. Two molecules become one. Okay, can you see two molecules become one? They join, right? Because nitrogen only has 7 electrons. It needs one more. So each nitrogen needs one more. This is considered to be a dimer. Okay, two same molecules join. Anybody can remember another dimer? The other one also we learned before is 2AlCl3. Oh, in chem bonding part 1 to form Al2Cl6. Okay, this is also another dimer. All right. So how do we learn it? Aluminum chloride has only 6 electrons around it. It needs 2 more. Okay, it needs 2 more electrons. So can somebody tell me where is the aluminum getting the 2 more electrons from? Anybody can remember? Where is Tarun? Tell me, where do you think the aluminum is getting the 2 more electrons from? This aluminum needs 2 more electrons, right? Where is it going to get it from? Yeah. Very good. Cl actually has 3 lone pair, right? But okay lah, we just show 1. Okay, there are 3 lone pairs. But this lone pair will form a dative bond to the Al. This Cl also, right, has a 3 lone pair, right? But normally we just draw 1. Okay, so the lone pair will form a dative bond to the Al. Okay, so dative bond, you know what's dative bond, right? Yeah. So now Al has 8 electrons, totally happy. Okay, totally stable. All right, so Al2Cl6. This is again known as a dimer. So, okay, so A level 3 dimers. Okay, this one, and the one we just learned. Okay, so dimer can be formed with a covalent bond, can be formed with a dative bond, can even be formed with a hydrogen bond. Okay, let's try next question.
Okay, benzene is a compound that's the formula is C6H6. Okay, it's a hydrocarbon. It doesn't like water at all. Okay, it's a non-aqueous solvent. You put non-aqueous, or I can say it's a non-polar solvent also. Okay, non-polar solvent. You know solvents, there are two types, right? It's either polar or non-polar, right? So polar, when I say polar solvents, right? Polar solvents generally is like water. Okay, water is a polar solvent, delta plus, delta minus, right? This is a polar solvent. So they're also non-polar solvents. So non-polar solvent are usually, for example, I think we learned this one, CCl4. This is a non-polar solvent. Okay, so polar compounds like polar solvents, non-polar compounds like non-polar solvents. Okay, so don't expect you to dissolve your sodium chloride, which is ionic, into oil, which is non-polar. Okay, they will definitely dissolve in polar solvents like water. Okay, any explanation? Just tell me why is this 120, like that's all. I think you all should get it. Give explanation why when ethanoic acid put in benzene, it becomes an MR of 120. That's all. Okay, you all should be able to write the thing. So in water it's 60, but in benzene it's 120. So what happens when it goes into benzene? You form a what? What happens when it goes to the benzene? You form a because it was 60, right? But what happens when you put in benzene? You form a what? That's it, double. Okay, so in benzene it will form a dimer. That's it. In water, it will not form a dimer. In water, ethanoic acids form hydrogen bonds with water, cannot dimerize. MR is 60, cannot dimerize. Okay, I'm going to show you why it can dimerize in benzene. Okay, this is a concept why it will dimerize in benzene. You all may not notice this, but this is the idea. If you look at this part of the molecule, right, this part of the molecule is polar. Because this part of the molecule has a delta plus and a delta minus. Again, this part of the molecule is polar. This part of the molecule is actually non-polar. It's a hydrocarbon. So you know why soap, you know it's soap, right? Soap actually has one part that's polar and one part that's non-polar. Okay, so I hope you realize that soap has one part that's polar and one part that's non-polar. That's why soap can dissolve in water and it also can dissolve in oil. Okay, so something like this, right? There's no non-polar and polar. So if I tell you benzene, actually benzene looks like this. Okay, but never mind. Don't get bothered about drawing for now. So do you think benzene, where would it be attracted? Do you think it will be attracted to the polar side or the non-polar side? What do you think? Okay, Jeremy, help me. Where do you think benzene will be attracted to? Which part? Will it be attracted to CH3 or do we think it will be attracted to COH? Yeah, so the benzene, it wouldn't want to go to the COH side. Benzene will just go to this side. It will just go close to this side, right? So you know what? This part is being totally what? Exposed, right? This part is totally exposed. So because the benzene only goes to the CH3, the right-hand side is totally exposed. That's why it will allow it to undergo dimerization. Maybe? Okay, that's why it can dimerize. Okay, because the benzene don't even go and interfere. But unlike water, water will interfere, right? Where does water go to? Water will go to the polar side. So water will surely want to go here. Okay, so water will interfere, so it won't allow it to dimerize. Okay, so in a non-aqueous solvent, this is the concept. Okay, in a non-aqueous solvent, ethanoic acid will dimerize, forming intermolecular H bonds. So the MR will be double. Okay, so I just drew for you what it means. I mean, so the benzene will just hang around the CH3 and it allows the COH, the polar side, to come together to dimerize. Okay, then the next part, can you please draw? Okay, this one I just more or less drew for you, right? But you all must draw yourself now. Draw a diagram to show the type of bonding present when acids dissolve in benzene. Okay, so draw the dimer. Okay, I'll tell you what's the marking point when you draw a dimer. Okay, then I think we'll do one more question before I think we end. Okay, everybody try to draw the dimer.
Okay, so marking point is how you draw the dimer, but the how you draw H1 basically. Okay, just copy from the slide. You can copy from the slide. Actually, if you ask me, it's all here again. Okay, but you have to draw this one. This one is from the dimer, right? Okay, do this. But R, of course, is just CH3. Okay, so that's the dimer. Okay, so can you just draw it out once and I tell you what's the marking point? Go through one more last part before we end. No, the drawing is not good. Not like that. See the bond there. The one line, C double bond O. That should help some of you. Can you draw this? Okay, this is one side, then you draw the other side. Okay, draw the other side. Yes. Okay. Draw not your. Okay. So the other side, the O you draw down. The O double bond O, right, is the other side. Double bond O here, then here OH. Okay. Okay, marking point for hydrogen bond. Maybe I didn't really say very much about it, but the marking point for hydrogen bond is this. H must put a delta plus. Did you do that? O must put a delta minus. Okay. These two marking point. I'm just going to highlight for you. Marking point will be this, and the lone pair. Okay. Show the lone pair on O also, right? Okay, so it must be logical. There's a lone pair attracted to the H that's delta plus. Then you show this. So this, then you label H point. That's it. Okay. Do the same for the other side. Delta plus on the H, delta minus on the O. Put the lone pair on the O, then draw this. So this shows you this is H point. Got it? So that's how we mark. And okay, the delta plus, delta minus, and the lone pair. Okay, so this is a dimer, right? Hydrogen bond both sides. And quite easy. Okay, so the whole entire MR is 120. Okay, it's double. Okay, let's look at one more question. Okay, let's look at one more question over here. So it's okay? Every good? Make sure you can draw it up. Let's do it over here. So same thing. Okay, let's run through one last question. I think then we'll stop. Okay, so over here, last part. Okay, we're gonna this is the last part right there. One part. Okay, last one. Okay, over here, I want you to see the differences in boiling point between boiling point and solubility of 2-nitrophenol and 4-nitrophenol. Okay, you all look at this. Maybe some of you have not learned organic chem, but what does this look like? Just for information, we see this this ring structure is actually like this. Okay, it's actually made out of carbon. If you want to draw it out so you know what it is actually, it's like 6 carbon in a ring. Okay, and there's an OH over here. Okay, and this is NO2. Okay, this NO2 can. And inside here, there's a double bond, single bond, double bond, single bond, double bond. So that's what it looks like. And every carbon has a H attached to it. Okay, so this is what we are drawing. Okay, we see a ring. That's why we sometimes we draw a ring, right? But it's actually like this. Are you me? Okay, so you know what's that? Okay, so that's called benzene. This whole thing is called benzene ring. When you see this, right, you're gonna learn this benzene. Just now it's C6H6. But just now I said C6H6. That's the one. Okay, benzene ring. Okay, so that's what it looks like. Okay, so let's look at 2-nitrophenol and 4-nitrophenol. Okay, so I drew out 2-nitrophenol already. So the question is, why does 2-nitrophenol has a lower boiling point than 4-nitrophenol? Okay, this is called the nitro group. This is phenol. Okay, maybe just for information, this carbon is called carbon 1, 2, 3, 4. So it's called 4-nitrophenol. This carbon 1, carbon 2, and this phenol, right? So it's called 2-nitrophenol. Okay, so just to give you an idea how we name it. Okay, so anyway, the question is this. So what happens? What are you breaking when you boil these two? Okay, what are you breaking? You're actually breaking hydrogen bonds, but not just hydrogen bonds. You're breaking intermolecular hydrogen bonds. So imagine when I boil this, I'm actually breaking this. I'm breaking this. When I boil it, I'm breaking intermolecular H bond. Okay, I'm breaking this if I boil it. Okay, but let's look at this molecule. This molecule looks like this. And if you realize something, there's a lone pair O, delta plus, delta minus. So this molecule within itself has intramolecular H bond, okay? Intra means within itself. This is intra, okay? Intra, but this is inter. So I want you to know the difference. But when I talk about boiling point, I'm breaking inter, not intra. Okay, I'm breaking inter, between molecules. Okay, so the idea is this. So the concept is this, right? So if you do form intramolecular hydrogen bond, you know what? If this H form intramolecular hydrogen bond, this H cannot form intermolecular hydrogen bond. It cannot form anymore. So which molecule would have more intermolecular hydrogen bonds? Which molecule? 2-nitrophenol or 4-nitrophenol will have more intermolecular hydrogen bonds? Ali? Again, if you form intramolecular hydrogen bond, this H cannot form intermolecular H bond. So which molecule will have more extensive inter? And that's the answer. Okay, this guy will have more extensive intermolecular H bonds. Okay, due to the so let's see. You can just read through and you understand. Due to the formation of intramolecular H bond, 2-nitrophenol has less sites. Why less sites? Because this H cannot form cannot form inter anymore. Less sites available for, in fact, if I will be more specific, for inter. If you want to be more specific, for intermolecular H bond. Okay, with other molecules. So that the intermolecular H bonds are less extensive. This guy is less, less extensive. Less extensive intermolecular H bond. Okay. So I think let me see my drawing. Did I draw? Is my drawing good over here? Okay, no, this drawing is not good. Later we'll look at another one. Okay, so actually I drew for you the intramolecular H bond. Okay, so take note of that. Okay, one more concept. So again, this one has a higher boiling point because it forms more extensive intermolecular. This one less extensive. Then this is how you write it. Less sites available for intermolecular H bonds. Okay. Okay. Last part here. So the next one is solubility. Actually, the same concept. So when is something soluble in water? If it can be very soluble in water, means it can form. Listen, you can write down. It can form H bonds with water. H bonds with water. So to be soluble, it must be able to form H bonds with water. Okay, to be soluble, it must be able to form hydrogen bonds with water. So again, if this H, right? Again, same concept. If this H forms, if this hydrogen forms intramolecular hydrogen bond, right? Can it form intermolecular hydrogen bond with water? Cannot. Good. So this one become less soluble also. Okay? Because it can form less extensive intermolecular H bonds with water. So actually my drawing here is I think it's okay. Look here, just to show you, just to highlight how many H bonds with water. Okay, like this guy, this O, right? Okay, maybe I'll just show you very quickly. This lone pair of this O, right? Hydrogen bond. Okay, so this OH form H bond here, H bonds with water. Okay, how about this guy here? Okay, so you notice over here, this OH, right? This OH, right? I only form hydrogen bond with water here. But the H, notice I didn't draw anything here. Notice I didn't draw anything here. It didn't form H bonds with water because it already formed H bonds with itself. Okay, so you look at how they drew it. Here, hydrogen bond, here, hydrogen bond, right? Here, how many? 1, 2, 3, 4. So this guy can form more extensive H bonds with water. This one less extensive. Why less extensive? Because this hydrogen cannot be used. Okay, this hydrogen cannot be used. It forms intramolecular H bond. Got it? Right? So that's the answer. Okay, less extensive H bonds. So over here they wrote down less extensive H bonds between this and water. So it becomes imply what? Less soluble. Okay, let's do one last slide and then we are done for today. Okay, one slide only. Okay, it's all about this concept. Okay, and the model answer, please try to write the way they wrote it. Okay, last slide. Okay, maybe you all just tell me which one has a lower boiling point. I let you copy down the answer. Then later on, this one you do yourself. Okay, which one is a lower boiling point? Amandia? The left one. Okay, good. Yeah, very good. This is the left one. So this one can form intra H bond. Okay, so we can write this down very quickly. Same concept, cut and paste from the notes. Due to the formation of intramolecular H bonds, I just do for you. Less sites are available for hydrogen bonding with other molecules. So intermolecular hydrogen bonds are less extensive. Imply this guy have a lower boiling point. Is okay? Very easy, right? So once it forms intra, it cannot form inter. In terms of like the H and O. Okay, the H and O cannot form inter. This one, do it yourself. If I help you one, then you do the other one. Okay, I want you to do me a favor. Explain and illustrate your answer. Illustrate your answer. So what I mean by illustrate answer, I want you to show me draw for me the intramolecular H bond. How will you draw it? Okay. Okay, last part, then we stop. Okay, illustrate your answer. So see how you can draw the intramolecular H bonds. Okay, it'll be good if you can show me your illustrate your answer with the drawing and then explain. Okay, illustrate your answer with the drawing and explain. Okay, who has a lower boiling point? Malic acid or malic acid? Maybe I just want to point out something. Is this hydrogen bond? Everybody, is this H bond? Is this H bond? Is this H bond? Is this H bond? Jachan, is it H bond? Ellie, is this H bond? Dylan, H bond? Dylan, is it H bond? No. Jeremy? Okay, very important. You see this H? Is it attached to FON? Not H bond. But a lot of people draw this as H bond, but this is not H bond, okay? I'm telling you this is not H bond, okay? You draw like that, it's wrong, okay? This H is not attached to FON, this is not H bond. Okay, so yeah, where's the intramolecular hydrogen bond? I'm going to just tell you, and I want you to try to draw it out. Draw it nicely. Show me that this one and this one can form intramolecular H bond because they are on the same side of the molecule. This side and this one cannot form intramolecular H bond because they are on opposite side of the molecule. Okay, so the one that can form intramolecular H bond is this two. But can you try to draw it in a nice way? I mean, the way they draw it is not nice, but you all must draw a nice way to show me that it can form H bonds, intramolecular H bonds. Okay, I'm going to show you now. It's okay, done. Okay, so over here, you see, the way I draw it, you must realize I draw this carbon as trigonoplanar. Very important because it's trigonoplanar. See? Okay, this part here, I'll probably draw like that. Okay, you see, I'm going to draw the trigonoplanar still. I'm not kidding you. I'm just drawing trigonoplanar still. I draw like that, can? And easily you can see that this H is delta plus, this O is delta minus, and there's a lone pair on this O. It can easily form intramolecular H bond. Are you me? Can you see that already? Okay, because they are so close to each other, they can form intramolecular H bond. Okay, but the other side are not possible because they are on opposite side of the molecule. And of the opposite side can. Okay, same side can. Okay, so that's it. This is fine. Okay, due to the formation intramolecular H bond, same concept. I think you don't even have to copy that. It's the same thing. I mean, exactly the same thing. So then this causes malic acid to have a lower boiling point. Okay, all you need to do is draw this, and then everything is the same. Are you me? Got it? Okay, so I'll stop here. Okay.